Okay, so we begin today the study of the systems of differential equations, the last major chapter of the class. Toward the end of the class, we're going to have two sections on nonlinear systems, but we will not be focusing too much on that. So for the remaining part of the course, most of the work will be focused on dealing with linear systems of equations. Before we delve into the linear systems themselves, we should go over briefly on how to write general systems of differential equations, and also how we plot the solutions, how equilibriums or constant solutions look like, what constitutes and how a stable equilibrium looks like, and so on. Just so you know, at the end of this lecture, there will be a presentation on the computer as part of this lecture. So make sure you go over that part of the lecture and run those examples on your own with Maple, with the plotter. Make sure you do that, because it will make much more sense once you actually get the feeling of on the computer on how things look like. So we will be focusing on systems of two equations. So systems of differential equations with two equations in which now we have two dependent variables. Which you can denote by any letters you want. I mean, typically I'm going to denote them by x of t, y of t. And remember the convention that once you understand that these are the dependent variables, you don't need to write of t all the time, just to avoid writing too many parentheses, right? So normally I should write here, if you remember, at the beginning of the class, right? I mean, if you were to write these as functions, you should write x prime of t equals f of x of t, y of t, and maybe t by itself. So we don't do that, again, just for simplicity, as long as, again, we understand perfectly well which of these are the dependent variables. And t is the independent variable, as before, is the time variable, typically, right, in dynamical systems. So t is the independent variable. So the first thing to discuss is how do we actually sketch solutions of differential systems. You may think that the only way to do it is just like for single ODEs, for instance, to plot x with respect to the time t. But in that case, and you could do that, and you should do that basically if you need to, if you actually need to track both the values of the dependent variable and the time value, then you have to basically work with two graphs in parallel, right? But it may be actually not that revealing in terms of the overall dynamics of the system if you actually have to track at the same time two graphs, right? Because as t moves, at the same time x and y change their values. And you may want to have an overall idea on how the values of x and y change in time. So maybe not the actual value of time when that happens, but the overall change in x and y. I should probably make a comparison here with the phase line on the first, on the single ODE. Remember, at that time, if you didn't actually care about the time value, but only how the solution moves, I mean how the values of y change, you would just basically write the y-axis and maybe the equilibrium points, and then with arrows you indicate how the solution changes with respect to the equilibrium points. Does it increase? Does it decrease? Does it approach an equilibrium point or not? So for single ODEs, if you care about tracking only the value of the dependent variable, you only look at the line, the so-called phase line. So by the same token, for systems of differential equations, if you don't care about the time value when a certain value happens, you could simply look at just the values of the dependent variable by sketching both x and y against each other. So basically you sketch the solution as a parametric curve, in which for every time t, you're going to have a point in the plane of coordinates x of t, y of t. So as time changes, this basically way of representing the solution will give you a motion in the plane. For example, here could be another point at a later time, let's say x of t plus h, y of t plus h. right? And that's why you have also an arrow. You can indicate by an arrow how the solution moves as t goes from 0 to infinity or backwards in time. So this type of representing the solution is called the phase plane. The plotter, when you run the plotter for systems of differential equations, this is the phase plane. And when you run the system for the first time, before you actually feed into the system an initial point for the solution, you'll see a bunch of arrows filling in the plane, the phase plane, which are essentially tangent vectors. So these are the tangents to the solution, to the solution curve, or to the solution, let's put it this way, to the solution trajectory. Right, because the solution looks like a trajectory or a motion in the plane. Let me write down this. I think that's fine. Yeah, it's a little bit out of range. So that's the default way of representing solutions in the plane. Again, it will be much more clear once you run the examples with the plotter. But even without the computer, we can tell quite a lot about how we have a feeling on how the solution essentially changes, how the solution moves along the trajectory, just by looking at the differential system, and in particular by looking at the sign of the derivatives. So one particular class of systems that is very suitable for this type of analysis, basically just looking at the sign of the derivatives and figuring out how the solution changes in time, is the so-called autonomous system. So an autonomous system is, we had this definition before, by the way, so it's a system in which the right-hand side only depends on the dependent variables. So it doesn't depend on t explicitly. So it's in the right-hand side you have only x and y. We're going to go over an example right away after going over this discussion. So this is an important class of systems, because if you want to get an intuitive idea on how the solution changes, you will realize that it depends only on the sign of x and y. So if you know your location in the phase plane, that is to say, if you know the value of x and y, you can simply plug it in the right hand side, and depending on the sign of x prime and y prime, you know how the solution changes. Just like in the single ODE, right? In a single ODE, you just look at the sign of the derivative, y prime, and you know it goes up or down. Now here, because you have two dependent variables, then obviously you have to track two signs at the same time, right? I mean, because you have two derivatives. So you have several cases with respect to how these arrows look like. And keep in mind that now, to say that x increases, it means that the movement is from left to right, because you decided to plot the x value on the horizontal axis. So if x prime is positive, that indicates a movement to the right hand side. If x is negative, it's to the left side. But at the same time, you also go up or down depending on whether y prime is positive or negative. So you have lots of combinations basically in terms of direction of motion. I mean, overall, basically, you can go 360 degrees, right? I mean, the direction of movement could be anywhere around that point you're located at. So to illustrate this briefly, suppose that, I mean, let's do actually a classification of how the arrow looks like depending on the sign of x prime and y prime. So let's see the direction here of motion on the solution. So if both derivatives are positive, that means x increases to the right, y increases upward. So the combination effect of these means that the arrow points right and up. So if you run the phase plane, if you run the system with the plotter, and at that point the derivatives have these signs, then you know that the solution moves right and up. Or vice versa, or conversely, if you look at the arrow, you know immediately the sign of the derivatives just based on the direction of the arrow. So other possibilities, plus minus, so that means you still move to the right, but y decreases, so that means the arrow points like this, right and down. Let's say negative derivative for x and positive for y. That means x decreases, so you move to the left, and y prime positive, so y increases. So that means left and up. And then finally, if both are negative, x decreases, so moving to the left, y decreases. So combined, the effect is that the arrow moves or points left and down. Of particular importance is when these derivatives are equal to 0, because you will see later when the derivative is 0, that gives you a borderline in the phase plane between between two different signs of the derivative, plus or minus. So when it's 0, that's like a separation boundary between these two regions. So for example, what does it tell me if I know that x prime is 0, precisely 0? Well, if x prime is 0, it means x won't change at that point. So that means the motion is neither right nor left, but it can be up or down, right, depending on the sign of y prime. So basically you have vertical arrows. Again, it's vertical simply because x is on the horizontal axis, and x doesn't change, so there's no left and right movement, just up and down. So if x prime is 0 and y prime is plus, you're going to have an arrow straight up, and straight down if y prime is negative. And I hope you get the main idea. If you have, let's say, 0 derivative for y prime, the motion is neither up nor down, but it can be left or right depending on the sign of x prime. So if x prime is positive, the motion is to the right, but perfectly horizontally, right, because y prime is 0. And if y prime is negative, if x prime is negative, the arrow points to the left side. So that helps you basically how to analyze the motion in the solution space based on the sign of the derivatives. Now, intuitively, how would you represent all solutions? Well, you're going to fill in the entire plane with a grid of points. And what do you do after that? Well, after that, you're going to compute the slopes, x prime, and compute the derivative at all of these points by plugging in these numbers in the right-hand side, and then you compute the tangent vector. That's extremely tedious if you want to do by hand. The plotter does that for you, of course. But there is a better way of getting some idea on the direction of solution with with a paper and pencil, a little bit more efficiently than just like what I said, picking random grid points here and computing the value of x prime and y prime, because that means lots of points if you want to do that randomly. So the way to do this, and we're going to illustrate with an example before we move on to some other stuff. The way to do this is to recognize that if I want to look at the location of x prime positive, y prime x prime negative, so if I want to look at the location of the sign of x prime, that's going to be on one side or the other of the region when x prime is x prime is 0. So you could say that the curve f of xy equals 0. So if I set the right hand side of x prime to 0, that gives me typically a curve, or in more complicated cases, a family of curves. But this curve separates x prime positive from x prime negative. So you could think of that curve like a boundary. Again, it can be made of multiple curves because this function can be more complicated than just a nice single curve, right? But roughly speaking, if you set this function equal to 0 and you think of it as a geometric figure, that's basically essentially an implicit curve, right? Because you have y as a function of x. So let's, for simplicity, imagine that this is just a single curve, right? So at any point on that curve, x prime is 0. So then it stands to reason that on one side of it, x prime will be positive, on the other side of it, x prime will be negative. So I can quickly localize the region in the plane where x prime is positive or negative by simply plotting this curve. So this curve has a special name. It's called the nullcline. So the so-called x nullcline is f of xy equals 0. So you sketch this, and it's called x nullcline because it gives you the separation area between x prime positive, x prime negative. And the y nullcline, of course, is the curve g of xy equals 0. Again, I know that it may be a little bit vague once we get to an example, but try to understand before we move on with the next with the first example what we mean by this. This is just a fancy name. Remember, there was another kind of similar name. It was isoclines, for instance, in the single ODEs. They had a different purpose at that time. Remember, the isoclines were curves with a single slope. Nullclines are essentially curves of slopes of derivatives equal to 0. So on an x nullcline, x prime will be 0. So on an x nullcline, you will see only vertical arrows, up or down. And on the other nullcline, horizontal arrows, left or right. So let's actually illustrate with an example before we move on. And this example is specifically chosen so that the nullclines have a very easy to recognize shape. So let's look at yeah, so let's start with this one. X prime equals x minus y, and y prime equals x minus y squared. So I make it so that the nullclines have easy to recognize shape, right? I mean, if you look at the first one, if I set x prime equals 0, so the x nullcline, x minus y equals 0, that's just a straight line. And the y nullcline, y equals x minus y squared equals 0, that's going to be a horizontal parabola. Okay, so let's actually sketch these nullclines in the phase plane, basically. So this is x, this is y. This is going to be x equals y, and this is x equals y, but I'm going to write here x prime equals 0 because that's more important for my purposes, right? X minus y is the same thing as x prime. On this line, x prime is 0, because that, reinforces that this line separates positive from negative x prime. That's the purpose of doing this. The same manner here, x minus y squared equals 0 gives me this parabola. And we're going to actually find this intersection point. It's easy to see that it intersects at 1 and 1. That's an equilibrium point. We'll talk about that on the next part. They also it goes through 0, 0. And I'm going to indicate on this horizontal parabola that here y prime is equal to 0, because that parabola separates positive derivative for y from negative derivative. Okay, so how do we figure out the direction of arrows for all the other points in the phase plane? Well, you simply have to decide whether it's positive or negative, above or below this line, or inside or outside the parabola for y prime. So you could do this easily with a test value. That's the easiest and quickest way to do it. So, for example, if I'm above the line, we're looking at x prime, right? So if I'm above this line, I can pick an easy test point. You can pick any point above the line, but the easiest one is to think about is maybe a point on the y-axis. So you can pick a test point, let's say 0, 1, x equals 0, y equals 1, and you plug it into the nullcline, and that's going to be 0 minus 1, which is negative. So I know that above the line, x prime will be negative. So what does it tell me about the motion of the solution? It tells me that above the line, the arrows will point to the right-hand side. They may be up, they may be down, depending on whether you are inside or outside the parabola, so depending on the sign of y prime, but they will point, did I say right? I forgot what I said. So the x prime is negative, so its movement to the left side, right? Because if x prime is negative, it's going to be, so above the line x prime is negative, that means the motion is to the left side. So x prime negative above the line. So you could indicate this information by putting a label on the nullcline. So put a horizontal arrow to the left of that line to indicate that if you're above the line, x prime is negative, that means it moves to the left side. So again, it could be up or down, but in this region above the line, the motion is to the left. And of course, if you are below the line, the motion is to the right-hand side. So again, this is just a label. It means that anywhere below the line, arrows will point to the right-hand side. Okay, so the same analysis for the parabola. Let's pick a test point outside of the parabola, the same thing. So you have to make sure you pick a test point either outside or inside the parabola, depending on what you want to test. I can use the same point here to figure out the sign of y prime outside of the parabola. So what happens here if I plug in x0 and y squared into the second nullcline? Again, it's negative. So that means y prime is less than 0 if you are above the parabola. Now y prime less than 0 means it decreases. It means that if you are above the parabola, the motion is downward. If you're below the parabola, the motion is upward. So now at any point in the plane, you use the combination of these two informations to figure out the direction of motion. So for example, let's say you are a point, let's pick a couple of points. Let's say here inside the parabola. Say I have an example here. And let's say a point right here. So you see both of these points are below the line, below the x equals y. So that means the motion is to the right for both of these points, because if you are below the line, x prime is positive. But because this one is inside the parabola, the motion is also upward. So inside the parabola is to the right and up, outside the parabola to the right and down. And you should run this example with the plotter just to convince yourself. Yeah, so right hand side, motion to the right, but y prime positive inside the parabola, y prime negative outside of the parabola. So for example, if you are with a point right here, because you are above the line, motion is to the left. Outside of the parabola, motion down, so left and down. And we're going to run another example on the second part with similar type of analysis. So this is just a brief way of how to figure out the motion of the solution based on the just without the plotter, based on the nullclines, if you can sketch them, of course. So as I said before, on the nullcline itself, the arrows are vertical or horizontal, right? So for example, all the points you pick on the actual nullcline here, arrows will be either up or down vertically, right? Because that means x prime doesn't change, it's 0 on that line. So for example, if you are right on this nullcline, the arrow will be perfectly vertical and downward because you're still above the parabola. So y prime will be negative on this area. If you're here, y prime will be positive, but it's going to be a perfectly vertical arrow because x prime is 0 there. On the parabola, arrows will be horizontal because it means that y prime is 0 for the for that parabola. So for example, if you are right here, because you're below the line, the arrow will be perfectly horizontal but pointing to the right hand side. And if you're here, I don't want to make a mess here, but the arrow here will be horizontal but pointing to the left if you pick a point right here, which is above that line. So we're going to move on with another example shortly, in which we analyze this these nullclines. But again, the real way to, the best way eventually to figure out everything on how this looks like is to actually run these examples with a plotter. So make sure you watch that presentation at the end on the computer with Camtasia. Before we move on to the next part, let me define briefly what an equilibrium solution means. It's a similar definition as for single ODEs. So an equilibrium or constant solution is a point AB such that x prime is such that f of AB equals 0 and g of AB equals 0. Remember the notations here in the system here. So that means a point in which both derivatives are 0. So let's put this in parentheses. Both x prime is 0, y prime is 0 at that point. So it's a point in which both derivatives won't change. And so notice that by default, any equilibrium point will happen at the intersection of two nullclines. That's very important to remember, because each nullcline represents a derivative equal to 0 by itself. Taken together as a system, they will provide you, if any exists, they will provide you the equilibrium points. So the equilibrium of the constant solutions always appear at the intersection of the x nullcline and y nullcline, if such a point exists. You will see examples at the end that there could be no equilibrium points, could be only one, could be two, like in this case, right? So basically, in this case, if you look here, it's easy to see that 0, 0, and 1, 1 are equilibrium points. When you solve this as a system, if x minus y is 0, y is equal to x, you plug it into the second equation, and you can factor out, and you get x equals 0, x equals 1. We're going to go over other examples like this, but you can see here clearly that the two parabolas in the line x equals y intersect at 0, 0, and 1, 1. So again, visually, they always appear at the intersection of two nullclines. The plotter I'm going to use in the demonstration at the end of today's lecture will actually plot the nullclines for you, so you can clearly see how many equilibrium points you have. So in the second part, we're going to move on with another example of a system, and at that time we're gonna do not only the nullclines and this analysis of the arrows, but we're gonna talk about how to find equilibrium points if possible, and whether in how to check the stability visually, as much as we can do here on the board, because most of these questions should be inferred from the plotter, at least for this introductory section. So stay tuned for the second part.